Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 26, 2026, just yesterday. It introduces a new inference system that improves online serving throughput by an average factor of 1.96 times, effectively nearly doubling performance by utilizing idle bandwidth on decoding engines. The paper is titled DualPath: Breaking the Storage Bandwidth Bottleneck in Agentic LLM Inference. And as we'll see later, the implications for handling long context agentic workloads are quite significant. Figure 1 visualizes this bottleneck and the solution side by side. On the left, the standard architecture shows the prefill engine struggling. Its connection to persistent storage is saturated at 100% utilization, marked by the large red arrow. This forces the GPUs to sit idle at just 40% utilization, even though the nearby decode engines have spare bandwidth. On the right, DualPath fixes this by letting decode engines also load data and transfer it to prefill nodes. By using both paths, the system feeds the GPUs faster, driving utilization up to 80%. So, Figure 2 illustrates this specific workload pattern that creates this bottleneck. It depicts a typical agent trajectory where the conversation history, on the left, has already accumulated 30,000 tokens. In the current turn on the right, the model only receives a small update, about 300 new tokens from a tool output. This imbalance means that over 99% of the prompt is reused context. Consequently, the system must load this massive key value cache from storage for every step, which confirms that storage bandwidth is the real limit. While Figure 2 showed the reuse pattern, Table 1 quantifies the resulting pressure using a metric called the cache compute ratio. This measures how many gigabytes of history must be loaded for every petaflop of computation needed to process the new input. Look at QN 2.532b at the top. It demands huge bandwidth relative to its compute, with a ratio exceeding 100. Interestingly, even for the massive DeepSeek v3.2, the ratio is notably higher than its predecessor, DeepSeek v3. This happens because newer, efficient architectures reduce computation, which paradoxically makes the storage bandwidth bottleneck even worse. So having identified the bottleneck, Figure 4 details the mechanical solution. On the left, Panel A shows the standard prefill engine read path, where the prefill node pulls data directly from storage through its local interface. On the right, Panel B introduces the novel decode engine read path. In this scenario, the decode node utilizes its idle bandwidth to fetch data, which it then ships to the prefill engine via the high-speed compute network. This effectively pools the storage bandwidth of the entire cluster, preventing the prefill node from getting overwhelmed. Well, Figure 4 explained the mechanism, and Figure 7 now presents the payoff in offline inference speed. The charts track job completion time for 3 models, with lower bars indicating better performance. The middle row, representing the massive DeepSeek 660B model, is particularly revealing. Here, the dark orange DualPath bars are nearly identical to the gray Oracle bars, which simulate a theoretical system with zero I/O delay. This implies the new method successfully removes the storage bottleneck, whereas the light orange bars for the basic version and the blue bars for the SGL baseline show significantly higher latency. So, Figure 7 established the speedup, and Figure 12 breaks down the sources. The right panel starts with the basic baseline in beige. Adding layer-wise prefill helps, but the green bars show that DualPath loading drives the most significant drop in job completion time. Ideally, we want to see this stability online too. The left panel confirms this. At a high load of 0.25 agents per second, the basic approach is dominated by red scheduling delays, meaning requests are stuck queuing. DualPath eliminates this bottleneck, keeping latency low even under pressure. Alright, Figure 12 proved the efficiency, but does it scale? Table 3 answers this with large-scale experiments using up to 1,152 GPUs. In the offline section, scaling the workload from 2,000 to 48,000 agents keeps the job completion time nearly constant at around 3,200 seconds. Similarly, for online serving, the bottom rows show that increasing the cluster size boosts throughput by 22 times, reaching 8.8 agents per second. Crucially, latency metrics like time to first token remain stable, confirming linear scalability. Wrapping up, 2 key takeaways stand out. DualPath turns idle network capacity into a performance multiplier, effectively doubling throughput by redistributing storage traffic across the entire cluster. This approach is becoming essential because, as models get faster and agentic workflows grow longer, the primary bottleneck is shifting from computation to storage I/O. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.